Okay, so we stopped at the time where we were talking about the differential equation of IV infusion, which is equal to R positive minus KXB at certain time at certain time. This is rate of elimination, and this is rate of infusion. This is zero order, and this is first order. Okay, for the profile, if you go to your slide number 11, okay, you'll find that we have rate versus time. Okay, if you remember when we were talking before about rate versus concentration, rate versus concentration, right, for first order, for zero order, okay, we had this profile here and we had this profile here. So according to the rate, if we are having the profile of rate with time, if we are having both of those together, the first order kinetic of the elimination will give me the rate of linear, right? We call this linear. And then the rate of this zero order will give me something like this, right? This is again the rate. So this is related to infusion and this is related to elimination. But we have both of them together. So what will happen that with time, as the drug is there, this will be constant. The drug is infused directly in the body. This will be constant, so it will not change with time. Okay, but this, the rate of elimination will increase linearly, or it will show at its linear. I will let you know what is the profile that we have until it will increase. Okay, until we reach the point that rate of elimination equals rate of infusion, then so we will have this. Okay, so as overall profile, that's what we will have. We will have increase of, we have both of them at time equals 0. We have infusion, elimination. Once the infusion starts, elimination will start. Okay, we have both of them together, but the rate will start. This is the total. This color is the total. Start to increase. It will not continue because the infusion will be equal the rate of elimination. As total, what we will have, this is whatever is happening here. So it's the change between both of them. So at this time, which we call it steady state, or we call it the plateau, or just as double S, at which the rate of infusion equals the rate of elimination. Okay, rate of infusion equals the rate of infusion. Okay, infusion equals the rate of elimination. This is rate. Again, if we have the profile as concentration versus time, again we will have this profile, okay, which is a result of whatever is happening here. So we will have increase in the concentration until we reach the steady state, and this is time to reach the steady state. Okay, usually, as we know already about steady state, or about whatever the target concentration that we have, this is called the steady state concentration, or clinical concentration, or target concentration, as we mentioned here. Okay, so this is your model graph for IV infusion. Again, we have first order elimination rate constant and zero order infusion. So again, if we go back to the idea of minimum effective concentration and minimum toxic concentration, if you know details about the therapeutic range of the drug, we may have this, which is subtherapeutic, or we may have this, okay, which is toxic or supratherapeutic. So we have this as toxic, and we have this as subtherapeutic, okay, concentration, or not effective, and this is the effective. So how we can deal with this, we will talk about it depending on whatever that we have in the equation, but you need to know that what we usually need, which is our steady state concentration or target concentration, we need the concentration to be as magnitude within the time that we need between the minimum toxic concentration and minimum effective concentration. Okay, we don't need this and we don't need that, but we can control it according to different things. We will talk about it in a minute. Okay, for steady state, for sure this is steady state and this is steady state here, but this is our desired steady state or clinical that we need. So it's a steady state in each one of them in which the rate of absorption equals the rate of elimination. Okay, so when we want to go back, if we want to go back to the equation that we have, so at certain time over, no, not over, it's as it is, and this is your, okay, so we have differential equation, okay, this is the rate of infusion, zero order, this is first order rate constant, this is the amount and the drug in the body, and this is the rate of change that we have in the body. Okay, remember that we can write the same equation as dxp over dt equals k naught, right? It's the same because k naught is equal to r. Okay, and this is what you have in your 16, the slide number 16. Okay, this differential equation, we need to do integration for this equation, which usually we said that we will use Laplace function or transforms to change the differential equation through different functions to have equations that we can deal with. So what we will have, let's start with x at certain time equals r over k time. Okay, so amount in the body at certain time equals rate of infusion over first order rate constant 1 minus exponent to the power of rate constant, first order elimination rate constant, and this is the time of infusion that I'm interested to measure the amount in the body at that time. Okay, for sure if we are talking about first order disposition, this will be, if I just divide by Vd, it will be equal to concentration in the plasma at certain time, which is equal K, right? I just divided by Vd, or R over total clearance, right? So we can notice that the concentration in the blood, if we have the infusion model, depends on the rate of infusion, the total clearance, or K, which is rate of rate constant, elimination rate constant, and apparent volume distribution, and the time of infusion or the duration of the infusion that we are talking about. So those are the factors that's affecting the concentration in the plasma. This will be your model equation. Okay? If we go back to the idea of the steady state versus time, when we are talking about steady state concentration, it's the same as concentration that happens when this at time equal infinity, because we said that steady state happens when the rate of infusion equals rate of elimination, okay, which is here, starting from here. Okay, so or when the change in the amount over time or change in the concentration over time equals 0. This theoretically happens at time equal infinity. As all the kinetics that we know, we can't reach it, this experimentally. So we call the steady state concentration, which is at infinity time, is the theoretical or true steady state concentration, which is we can determine it mathematically, but we can't determine it experimentally. Okay, so this is the idea about steady state concentration, which is happening at time equal infinity, which we call it as true or theoretical concentration. This as concentration, can I determine it if I want to know it mathematically when this happens, or as a concentration at certain time equals R over K Vd. I want to determine the steady state concentration, which means I need to substitute what? Infinity here. If we have it as infinity, we will lose this term, 1 minus this, it will be 1, so it will be R over K multiplied with Vd, which will be equal R over total clearance, which means that steady state concentration is proportionally related to the rate of infusion, and it depends also, this is one, depends on the rate of elimination constant and apparent volume distribution, or the systemic clearance. Okay, so if we are talking about the idea of we having the same individual and all the stuff that we were talking about, same physiology, same pathology, and all the assumptions for first order kinetic, which means that K, Vd, and clearance are constant, then accordingly the steady state concentration mainly will, under those conditions, will mainly depend on R, which is K naught, which is the rate of infusion, mass per time, right? So if we'll go back to this, okay, for this graph, according to whatever you know here, it means if we are having the steady state, that is equal to R over K Vd. If we consider this constant because we have first order kinetic, it means that I can control the steady state that I will have by changing the rate of infusion, which means if this is the desired concentration that I want, decreasing it by half will decrease the steady state concentration, okay? Increasing it by twofolds or double it will have increasing the steady state concentration. Let me write it. This is the thing that you are having on your 21 slide, okay? In other words, if I will have this, let's say, if we have let's consider it this, I'm decreasing the infusion rate by half, the concentration is decreased. This concentration is decreased by half because it's proportionally related. If I have the concentration doubled, or let's say it's more than doubled 4 times. So if I have increasing R 4 times over K multiplied to VD, by default, this will causing the steady state concentration to increase by 4-fold. Okay, so this is what I'm talking about. This, I thought that I'm using the same color, but I'm not, but it's fine. And here, it's what I'm talking about in this case. Okay, so we can control the concentration, the steady state concentration that we have and that we need and that we are having it as desired or target concentration by controlling R that we have, which is the rate of infusion, which in other words, what you are infusing in your patient. But in all cases that we have, whatever, if we are subtherapeutic or supratherapeutic, this changing R did not change the time to reach the steady state. Okay, so time to reach the steady state is independent on R changes. Okay, whatever R is changing, either it's R as it is or I just decrease it or increase it, the time to reach the steady state for all of them will stay the same. Okay, and I will stop it here and then we'll continue about practical steady state.